All right, so let's now talk about conservation of energy. Before we do that, when we say conservation of energy, we are actually talking about mechanical energy. And what is mechanical energy? It's going to be the sum of your kinetic energy and your potential energy. So a lot of the time you'll see, E is whatever, KE plus PE. Sometimes, depending on the notation, sometimes just K plus P to simplify. Sometimes P is U, just, depending on what you're looking at, just be careful because the notations vary. Yeah, this is usually actually a U, I think, when it's just a one letter. So this can also be a symbol for, this is supposed to be a U for potential energy. So once again, if we're only looking at conservative forces, and this is what we're going to mostly be focusing on. So we're going to be looking at systems that use gravitational force or spring forces. But if that's the case, that quantity over here, so E, which is the sum of potential and kinetic energy, is going to be conserved. So in other words, that means that if I look at the change, so again, delta E, all right? And if I just remind you, this is, if we use a delta, it's the final minus the initial. All right, so that is going to then be equal to 0. It doesn't change, okay? So a conservative, for any conservative quantity, you can write that the delta of that quantity is equal to 0, all right? Again, delta being final value minus initial value, meaning that I'm looking at two events. I'm looking at what's going on, for example, here, this would be my initial, and then I'm looking at what's happening here, this is my final. If we say the only force acting here is going to be, I'm providing the work, but then the only external force is going to be gravitational, or if I let it go, it's really in free fall, and then that's the only force acting on it. We're going to see that we have conservation of energy. When I'm actually lifting it up, that's not a good example because I'm providing work, and so I'm actually increasing the energy of my system, but it's coming from another source. But if we're just looking at the pen, it has right now a potential energy. I let it go. The actual energy of the pen as it's falling is going to be conserved, and we'll see how that means for the motion of the pen, which we already are so familiar with, right? Free fall. So this relationship, so saying that, okay, so if my mechanical energy is the sum of my kinetic and my potential, I can then write that the change, if I look at the change in potential plus the change in kinetic, it's going to be the same. Another way to look at this is to say, all right, so if I look at my delta E, okay, so it's going to be, once again, E final minus E initial. So that's going to be according to what we said. So KE final plus KE initial, my kinetic energy, right? That's not what I meant to write. So plus PE final, sorry. So this, I'm going too fast here. So this is my final mechanical energy minus my initial. So we would take then a look at the initial kinetic energy and the initial potential energy, all right? So again, this is my initial. And you can see that then I have KE final minus KE initial. That's the same as a delta KE. PE final minus PE initial. That's going to be my delta PE. And that whole thing needs to be equal to 0. All right. So different ways to think about it. But that means that if I add up the change in potential energy and this change in kinetic energy, they're going to cancel out. And that means that conceptually, right, if I gain potential energy, that means that I have to lose potential kinetic energy, right? And so we're going to be looking at some examples in this video. This law tells us that the energy is not created or destroyed, all right? It's only just transferred. So in this case, we're looking at energy going from potential to kinetic or vice versa. And if we look at the overall, the sum of potential and kinetic, it should always be the same. So what I'm going to do now is actually jump to the simulation to show you an example. So we looked at here, you know, what happens maybe with gravitational potential energy, but I also want to show you another system, all right? And we're going to have both. So masses and springs, and I'm gonna go jump to energy here. There is a link to go to this in Canvas if you wanna try it out for yourself. And so you can see that I have a spring over here and I have a mass. What we're gonna look at here is the values of kinetic energy, potential energy, so gravitational, elastic. I'm gonna say that there is no damping. So we're going to ignore any friction, any air resistance, and we'll see, we'll try to add some to see what happens. But for now, we're gonna see there's none of this stuff. And then that's your total, all right? So what we're expecting to see is that the total remains the same, and that as the mass is going to be oscillating on the spring, that there's going to also be oscillations in the values of kinetic and potential energy. So, and you can see that this is a good example because in this example, we're going to have both gravitational potential energy because the mass is going to change in height, but also a change in elastic potential energy because the spring is going to also be compressed and stretched. So just right now, I'm still holding the mass, so it's not oscillating, but I'm gonna stretch it out. You can see that as I'm stretching, I'm doing work. So I'm increasing the total energy of my system, right? So that's because I'm pulling on this right now, all right? And then I'm gonna let go. Once I let go, that's when the only forces are acting on the mass will be gravity and the spring force. So let's go and see. All right, so you may notice that the total does not change. You can see that kinetic is so you can also, I think, slow it down if you want, but the kinetic energy is showing, you know, its maximum when the mass is at its maximum speed. You can see that we definitely see the oscillations going with the height for the gravitational potential energy, and for the elastic potential energy, it depends on how much compression or stretching we have in the spring at any given moment. But if I add all of these contributions together, that the total remains the same. You can see that the potential elastic energy, the elastic potential energy is 0 as we're going through the equilibrium position of the spring. All right, so it's worthwhile to kind of, you know, look at the system. It's a really good summary of everything that we've learned so far, all right, in terms of looking at kinetic energy, gravitational potential energy, and even elastic potential energy. You can change various factors, so you could, you know, change gravity. Right now we are on Earth, but you could see how things would be affected if we move to another planet. You can look at here different things that will show you the displacement from the equilibrium position. This was the position of the mass if it was not oscillating. What I want to do also, so if you really want it, you could also make measurements to really check the calculations. And you also have a timer. So if you want to, but this is more if you want to count oscillations and whatnot, and we'll get to oscillations in a future chapter. So the only thing, the last thing I want to do here is take a look at damping. So what if I now introduce non-conservative forces? So damping is going to slow down the mass because of air resistance and other factors that so far we have completely ignored. Once I introduce damping, I want you to look at the total energy of my system, and you'll see that at that point, we're going to be losing energy, all right? So let's see, we introduce some damping. and you can see eventually it stops. So what we have is that we have that thermal energy, so that heat that took up some of that now, and then until it was not enough, and our spring stopped moving. All right. So I would encourage you to check it out for yourself, and try it out and try different scenarios and play around. You can also see that there's other tabs that could be useful. All right, and I'll stop here for this video on conservation of energy. And in the next video, we'll talk more about energy efficiency. We will also talk about power. How does it mean, when you're reading your electricity bill, and we talk a lot about power, but really just putting it in context and really understanding what it means. And we'll talk then about sources of energy. All right. Thank you. Bye.